Okay, I think it's time to start. So welcome everybody, and welcome back to microcomputer technology. In the last week, as a short repetition, we have started with the construction of our own 4-bit CPU, and yesterday in the lab, one group, or yesterday we have 2 labs, 2 groups have already started to work with the mnemonic code of our own 4-bit CPU. And I think this was the last slide that we have discussed last week, slide 71, where I have explained that if you want to enhance your ALU with some multiplication functionality, this is possible completely in hardware. And we have discussed this multiplicator that uses the same approach as we use if we want to multiply 2 binary numbers. So in the end, we are copying the first factor for all positions where there is a 1 in the second factor, and we have to left shift our first factor depending on the position of the digit in the second factor. And we have done this example together, and we have seen, okay, in hardware or in the binary system, a multiplication boils down to copying the first factor several times, make left shifts depending on the position, and then make an addition. And this leads to one possible implementation in hardware using half adders and half adders and full adders. Then we have discussed this matrix here, this structure that does exactly this. I've told you that the diagonal lines represent the shifting operation, what we are doing with pen and paper by simply going to the next column, is done here with the input to the full adder that's to the right bottom of the previous line. Then we have seen, okay, we can realize a multiplication like this, but we have also seen that in the end, multiplication is not necessary at all, because multiplication is a shortcut for addition. And we also, we do not need, for example, a power function, a power instruction, because power 2 power 5 or something like this is a shortcut to multiplication, and multiplication again is a shortcut to addition, so everything can be expressed as addition. And we have also seen that we are not needing subtraction at all, because subtraction means adding the 2's complement. So the so to say, the basic operation of all arithmetic operations is an addition. If we are able to execute an addition, and if we are able to represent numbers in 2's complement, we can execute, or we can construct all other operations based on this fundamental operation, so to say. Okay. The last row of application should be A0, B0, C. You mean here, right? Last row of multiplication, we have B0 times A0, B0 times. Yeah, this must be a B0, right? That's a typo. You mean this one, right?
Yes.
Yeah, you're right. Let me take a note here, and then I will fix this in the next version. Yeah, thank you. Thank you, Ryan. You're right. That's copy and paste error. Okay. Then we go ahead with the construction of our CPU. We have some general slides in between where I try to outline what we need if we want to realize the real world CPU, and then we try to do it in a simplified way for our own CPU. Yeah, here again, we see the block diagram for our CPU. And now we take a look at the registers. We have talked about the registers several times during the last weeks. And you know, okay, a register is a memory location within the CPU. The register set, or the set of registers, is limited. So I don't have an arbitrary number of registers. I have, in general, a power of 2, so 2 registers, or 4, or 8, or 16, or whatever. And each register offers a specific bit width, so a specific capacity. And this bit width, in the end, defines the architecture of the overall system. So if you're talking about a 64-bit architecture, nowadays very common, then the registers used offer you 64 bits to represent information. 5 or 10 years ago, the standard was 32-bit architecture, so the registers only offer 32 bits, and I'm sure we will see during our lifetime a lot of performance gains again in the end by enhancing the capacity of the registers. We have also seen, or we have also discussed, that the registers are the fastest memory cells because they are located directly in the CPU, and the CPU in general is operated with maximum clock speed. So within the CPU, you have the main clock speed, the key clock speed for the entire system, so 2.6 gigahertz or something like this. And therefore, everything that can be executed within the CPU, within the registers, will enhance the performance of your overall program, because the registers works with the highest frequency. If the register set is not sufficient, that means, for example, if you only have 2 registers, like in our own CPU, then you can only handle 2 operands at the time. And if you have more operands, you have to write this out to your memory. This is sometimes called swapping. This is called swapping. It's offered on the hardware level. It's also offered on the operating system level. So your operating system does exactly the same. So for example, if you have 16 gigabytes of main memory and you are reaching the capacity of your main memory, then your operating system will swap the main memory to your hard disk. So nowadays, the hard disk oftentimes is an SSD, a solid state drive. So the performance or the speed difference between the main memory and the hard disk is not so big anymore. But 10 years ago, when real hard drives were used, so spinning disks, there was a big gap between the speed of the main memory and the speed of the hard disk. And therefore, swapping always reduces performance because the hard disk is the slowest memory. This is also called swapping. So you can have swapping, or swapping can be done from the registers to the main memory, and it comes along with performance reduction, or it can be done from the main memory to the hard disk. So in the perfect world, in an ideal world, you should be able to execute everything in your CPU without swapping at all, and then you get the best performance out of your system. But for real world problems and algorithms, you oftentimes need to store, to save intermediate results, variables, whatever, on your hard disk, and then you read it back if necessary, if required. Yeah, here are two examples for register sets. On the left side, we have again our ARM version 8A architecture. So for this architecture, we can use 32 general purpose registers enumerated from X0 to X31 with 64 bits. And that's another architecture. We have seen 16 registers in our manual for our board, but here we have more registers, and we can also address the 32 least significant bits of these registers via W0 to W31. So we can distinguish between the entire register, or we can only take half of the register set. It's also possible depending on the architecture. It's not possible on all architectures, but here this ARM version 8A architecture offers exactly this functionality. We have some special registers, of course, because we need them for the execution of our programs. So we have the program counter. What was the purpose of the program counter? Can you remember?
To keep track of which instruction run, was that right?
Yeah, exactly. So the program counter is in the end a pointer to the next instruction that should be executed or to the current instruction. It depends on the implementation of the control unit, but I need one position where I keep state of the current execution of the program. So I need to count the commands, and the program counter exactly does this. It simply stores an address what to do next, which is the next instruction. The program counter also comes into play if I invoke a subroutine, for example, with a BL branch link in our ARM instruction set, because if I want to invoke a subroutine, this means that within my main memory, and the main memory is simply a table, that within my memory, I jump from, for example, line 200 to line 600. So I skip all commands in between, and I invoke the subroutine at a different address. And this means, for example, if I use branch link BL, then also the program counter has to be modified. The program counter has to be set to the target address of, or the starting address of my subroutine. Here we have a stack pointer. The stack pointer stores the address of the topmost element within my stack. So, for example, again, if I make a subroutine invocation, if I call a function, then all parameters that are passed to this function can be pushed on the stack. The stack pointer is manipulated, so it's, for example, incremented three times if I want to pass 3 arguments. And then the invoked subroutine has to read back these parameters, and it decrements the stack pointer again. So the stack pointer is comparable to the program counter because it marks a specific position in my memory to read the data that I need or to read the instruction that I need. The program status stores our flags, 0 flag, negative flag, carry flag, whatever. It depends again on the architecture. And we have an exception link. So this can be used, for example, if exceptions or error conditions occur, then it's possible to branch to a specific error handler or compensation function. And some architectures offer you a dedicated memory location to store this compensation handler, or to store the address where the compensation handler can be found and executed. We have also floating point registers, 32 floating point registers with 128 bits. And these floating point registers can be operated with SIMD instructions. So here we have again single instruction, multiple data. So we can execute one instruction on a set of these floating point registers in parallel. So we can manipulate several registers in one step. On the right side, we have an example. Neon is this functionality, or is this extension that offers you the SIMD execution. It's simply a marker for SIMD execution on the floating point registers. The term is not relevant to us. In the end, it's a marketing term. It's a marketing term, and we need to know, okay, it's SIMD execution. On the right side, we have the register set for an Intel 64 architecture. So maybe nowadays the most common architecture in your desktop PC. Also, AMD CPUs or AMD processors are based on this Intel 64 architecture. So in the beginning, my first PC was 386, for example. 386. Now you can take a look at Wikipedia and can calculate how old I am. So it's a long time ago. That was my first PC. And if you buy a PC like this back in the old days, there was always a label on the box, 100% compatibility with Intel X something architecture. So if you buy hardware, you buy compatibility with Intel, because Intel was the key player, was the main player in the market, and all software developers and all hardware developers focus on compatibility to the system. And then a few years ago, competitors rise in the market. So for example, you can today buy AMD processors, and they offer you nearly 100% compatibility with Intel. And some students and also some colleagues say, okay, AMD is much more better than Intel because this. And then some students say, no, Intel is better. And at the moment, ARM is on the rising branch, right? Because in your smartphones and in your mobile PCs, in your notebooks, everywhere are ARM processors. So there is always a competition between the different architectures. But I guess there will not be one architecture in the future. There will always be 2, 3, 4 key players, main players that offer an architecture, and you will have compatibility between the architectures, or you will have some kind of cross-compile. So for example, Apple offers Apple delivers you the cross-compiler for their new architecture. It's called Rosetta 2, I think so. Because if there is no compatibility, you cannot sell your new architecture. So a new architecture with no backward compatibility means there is no software that can be used, and hardware without software is not really fun. So for Intel, we can see 16 general purpose registers with also 64-bit width. We can also separately address the least significant bits of the first 8 registers, and The 8th register serves as a stack pointer. So we have again here the stack pointer. We have again some special registers. The instruction pointer, this is called RIP or program counter. The abbreviation is maybe not so good, RIP, yeah, we have an instruction pointer too. We have status register to store the flags. So you see the same approach in the end. Yeah? The naming is a little bit different, but we have the same registers. We have registers for the same purpose. We have also some SIMD registers. Here they are called XMM, not Neon, but XMM with 128 bits. And we have floating point registers with a 64-bit MMX extension. And these are 80-bit registers. Now you see in detail the registers differ. So we have different width, different addressing, different naming, and so on. But the overall purpose, how they can or how they should be used, is comparable between the different architectures. We will see in a second that for our own 4-bit CPU, there is not a problem, but a restriction. We only have 2 registers, and that makes it a little bit more complicated to solve problems, right? So if I have more than 2 operands, then I have to swap within our own 4-bit CPU. Yeah, the term accumulator, we have already heard this in the last week. There is one register that can be seen as the main register that is used most of the time and is from it's in the end a historical term. This register was called accumulator, or in German we simply say Akku, the accumulator. And the main operand, the first operand, is always stored in the accumulator, and the second one is stored in an additional register. We call it here in our CPU simply register A and B. A for accumulator and B for the second register. Yeah, the more registers available, the easier and more effective is to program the processor. You will see this in the lab. With 2 registers, you have to organize a lot of memory management by your own, because you have to write data out, you have to execute operations, you have to read data back from the memory. And this is a little bit, yeah, it's in the end effort. Yeah? You have to do it by hand. And if you have, for example, 60 registers, like on ARM, then it becomes much easier, because you can simply distribute your calculation between the available registers. Okay, it's a trade-off, because the more registers, the more complex your processor architecture becomes. So if you have more registers, your control unit also must support more registers. So if you want a very simple architecture, you reduce the components, you reduce the registers, then your programs will get bigger and more complicated, and vice versa. So if you make a very complex architecture with a lot of registers, your programs become easier. So it depends where you invest the effort. In the beginning, during the construction of the CPU, or afterwards as program. So if you want to sell CPUs, of course, you have to ease the life of your customer. So you have to offer more functionality, then your programmer gets happy. And happy programmer means you can sell more processors, because there will be more software for your architecture. Okay, that's all about registers. Yeah? We will see this in action in a second. And now we take a look at the control. Now it becomes very interesting, because now we get connection to the end of the first semester. At the end of the first semester, we have talked about the finite state machines, and the last sentence in the first part of the lecture notes was all PCs are a connection of hundreds, thousands, millions of Medvedev machines. Maybe you remember this. And I've told you, okay, we will see where the finite state machine is used in the second semester. And I hope today we can completely cover this. The control unit is, in the end, a finite state machine. Yeah, finite state machine, you have several states, you have transitions between the states, and the finite state machine, in the end, has some kind of memory, and you can react depending on all previous states. In the lab, we have realized counters, and we have seen that you can control your LED intensity, and also our CU, our control unit, is a finite state machine, to be honest, a very complex one, with a lot of states, with a lot of transitions, but I try to explain how it works in general. If you want to implement it completely, you will see also for this architecture, for this very easy architecture, it's a very, very complex control unit. Okay, the control unit coordinates time sequences inside the CPU. Time sequences means that the control unit drives the overall execution. So the control unit is responsible for, in the end, powering your entire system, and to reach a point where user code can be executed. You know, if you switch on your PC, then your PC starts with a so-called post. Do you know this term, post? Here?
I'm familiar with it, yeah.
Yeah, once again, please.
I said I am familiar with it, yeah.
Yeah, what's this abbreviation? What does it mean?
Or I don't recall what it stands for. Sorry.
It stands for power on self-test. Power on self-test. So if you switch on your PC, if you power your PC, then there is, in the end, a hardware check. So the circuits, the connections, the entire system is checked from an electrical perspective. And then there is one point where, in the end, software takes over. Yeah? And this initial self-check that everything works and that you reach the point when software can be executed, this is called post-power on self-test. And a few years ago, if there was a problem during the power on self-test, your PC gives you some beep sounds. Yeah? It simply makes some beep, 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 beep. And you have to take a look in the manual, and there was an encoding. So, for example, 2 times long, 2 times short means the main board has been exploded or something like this. Yeah? So there was an encoding, or hard disk cannot be detected, or keyboard is broken or something like this. So all components are checked. If everything is fine, your PC starts in the standard way, but then you reach a point, for example, memory location 0, when you want to execute software, and everything in between, this is power on self-test. Used to have PC which didn't start if a keyboard wasn't connected to it. Yeah, that was an old PC, right? Not a new one.
Yeah, I don't know, Celeron was it?
Yeah, Celeron, yeah. Okay.
Yeah. So it used to, if no keyboard was connected, it used to say, okay, connect one and then press F1 on the keyboard.
Yeah.
It made sure there is a keyboard.
Yeah, exactly. That's what I meant. So this is also part of the post. It simply checks all devices, internally connected devices, and if there is one device missing, you get a beep, and then it stops. And yeah, the control unit. Then after this post has been done, and you start with execution of software, then the control unit comes into play. Because the control unit then starts with memory cell 0 and drives the execution of your system. So on modern systems, you have an operating system, so you don't start with assembler code, but the instructions that set up your operating system, of course, are given in assembler code, and the CU is responsible to execute these commands until a point that you as a user can start working with the machine. Today, this is done very fast. If you go back to old Windows versions or maybe DOS or something like this, this can take minutes. Maybe take minutes to get a prompt to work with your system. Today, it's only seconds. Okay, so within your control unit, we have 4 important components. We have an instruction register, we have an instruction decoder, we have a memory address register, and we have the program counter. The program counter, we have already seen it. Instruction decoder, we will realize in a minute. Instruction register, we will also see in a minute. And the memory address register, this in the end is used to connect your main memory with the memory location within your CPU. We will see in a second how it works. So the CU always works in 2 phases, fetch and execute phase. We have seen this 2 or 3 weeks ago, and here are more details about the involved components and how the phases are organized. So we are starting from the command. Command means in the end instruction in mnemonic, and this command is interpreted or I cannot say executed because I need this term here, but it's interpreted and interpreted in 2 phases, fetch phase and execute phase. Fetching means that the CU reads the command from the main memory. So the command is available for interpretation, and execution means that the CU checks, okay, which command should be done. So it's an interpretation, and then the necessary operands are also read, moved to the specific registers. The command is executed, and the result is written back. This is given here on the right side. So the fetch phase contains fetching of the instruction and decoding of the instruction. And the execute phase contains fetching of the operands or one operand. It depends on the command, right? So there are commands with only one operand, there are commands with 2 or 3 operands. So we have to fetch the operands. We execute the instruction. So we, for example, calculate 3 plus 5. And then we have to write back the result. We have to store the result in the main memory again. And this is done completely within your CU. So the CU uses all components within your CPU. So the registers, the main memory, in the end, all the components are involved here. So what I missed, let me see. I told you this. Yeah, okay. Here is also the term Medvedev machine here. So the construction principle of this control unit is a Medvedev machine. That was the last type of finite state machines that we have seen in the first semester. So we have talked about Mealy machines, Moore machines, and we have also seen Medvedev machines. The main difference was that we use here a specific mapping from input to output. Maybe you remember there was an example with a D-latch, and if we use a D-latch for mapping input to output, then we can construct a Medvedev machine. Okay. So now we want to understand, okay, how are these components realized here? How does the instruction register work, the instruction decoder, and so on. And this is shown on the next slides. We first take a look at the instruction decoder. The instruction decoder tries to interpret a specific assembler code or a specific bit pattern. We have machine code in the end, and the instruction decoder tries to interpret this machine code. And let's start here with the example at the right side. If I want to execute add R2, R3, this is from our ARM instruction set, then you know add R2, R3 is executed like this. We add the content of register R2 and R3 and write the result back to R2. So if this instruction should be executed, then we have to do several steps. First, we have to connect our registers R2 and R3 to the ALU's input. So you remember from last week, our ALU is the only component that our ALU is the only component that can execute arithmetic or logic operations. There is no other component, so addition, subtraction, whatever, must be executed in the ALU. So if I want to add R2 and R3, I need a connection between the registers and the ALU because I have several registers. I have to select two and I have to connect them with the ALU. That means from the entire register set, here we have several registers, I'm connecting R2 with the first input and R3 with the second input. Because I need my operands, right? I need the operands to execute the addition. Then after I have prepared the operation, I can increase my program count because then I have already read the command. So the addition leads to a connection of the registers with my ALU inputs. Then I can increase the program counter because now I can execute the next command. And I have to set the ALU to addition mode. So the ALU offers you several operations, right? We have addition, subtraction, choose, complement, whatever. It depends on the instruction set. But if I want to make an addition, I have to switch it to addition mode. In step 4, after the addition is done, I have to store the result in register 2 again. That means the output of the ALU must be written back to register 2. This one, to register 2. And I have to set the status flags, so the flag bits, in accordance with the result. So for example, if in my register 2, if there has been -3, and in my register R3, there has been +3, and I make an addition, then the result is 0 and I have to update the 0 flag. So the 0 flag has to be set to 1. And after this, the instruction has been completely interpreted and executed. Then this one interpretation stops. Yeah? Then it goes to the next instruction. The next instruction is already addressed by the program counter, and then I have to do exactly the same operations or the same steps. I have to interpret the command. Depending on the command, I connect specific registers with the ALU. I switch the ALU to a specific mode, execute the operation, and write the result back. And the instruction decoder uses a special instruction register. The instruction register, or IR, this instruction register stores a copy of the command. So each command that should be executed is first copied to our instruction register. And in the instruction register, we have, in the end, a bit pattern. And this bit pattern contains the instruction code and an address part. And an address part, you can remember that we have special encodings for the commands, and sometimes we have operands or memory addresses, and also these addresses have to be stored and interpreted. And only the instruction code, it's here the first half, but must not be the first half. We have seen in the ARM instruction set that the bits can be interleaved. So you cannot say 8 bits for instruction, 8 bits for address. That will not work always. So it can be interleaved, and therefore we take out a subset of this instruction register and push this bit pattern to the instruction decoder. And the instruction decoder interprets the command. So it selects some registers out of the register set, it triggers the ALU, it updates the flags, it updates the program counter, and so on. And all of these manipulations of these update operations here are in the end hardware control signals. So this is not software. This is a wire to a specific component, and I trigger this component to execute a specific functionality. So here we have everything in hardware. So don't be confused. The assembler program, this is software. This is given by you as programmer, but the interpretation and the operation of the system, of the CU, of the ALU, this is completely done as a logic circuit. There is no software in between. So you have a physical logic circuit with a lot of components, a lot of connection lines, and then a bit pattern triggers this logic circuit to produce a specific output. Okay. So on the next slide, we see again the control unit in the overall layout of our CPU. This is a figure from Malz again, Computer Architecture or Rechnerarchitektur in German. And the control unit is shown here in this dashed box. We have the instruction register, the instruction decoder, the instruction pointer, and the memory address register. So the instruction register stores the current instruction that should be executed. The instruction decoder creates control signals to the ALU, to the instruction pointer, to to data buffer registers, to memory address registers. And we have an instruction pointer. This is the same as the program counter. This is equivalent. And we have our memory address register. This is the next instruction address or storage address of the data. So this, in the end, is a pointer. Okay, where's my next instruction, or where's my next operand that I need? Yeah, because I have to buffer or to store this information to realize the execution. So this is all within your CPU, and it's directly connected to the ALU. Here are our two registers, A and D, accumulator and register B. We have here an additional register set, but we have two main registers as inputs to the ALU. And we have here some data buffer registers to access the data bus, respectively the main memory. So the control unit in our overall block diagram, it's one black box. But of course, if you zoom in, then you see that the control unit is interconnected with all other components within your CPU. So this is a different representation, but you see if you rename the components, you will find again the same components as I've discussed in the beginning of the control unit. So then the control unit must be able to interpret different different command structures. The command structure again depends on the instruction set, so on the architecture, and it depends on the type of command. And there are two different characteristics that we can distinguish. We can distinguish between instruction addressing and instruction length. And we start with instruction addressing. So we have already seen that there are zero address instructions, single address instructions, double address instructions, and three address instructions. Here on the right side, we have corresponding examples. So a zero address instruction is, for example, the mnemonic RET or RET, that's the mnemonic for return. So this command, this instruction return, is always the last in a subroutine. So if you have invoked a subroutine with branch and you want to jump back to the invocation point, then your last command is return. Return will copy back the state that was there before the method invocation and starts over with the next command. This is, for example, an instruction from the 8051 CPU. So this was one of the very old CPUs we have seen in the beginning. There was a zero address instruction RET. And why we call it zero address? Because here there is no operand, no address, nothing. So return can directly be interpreted and executed without operands, without addresses. Then we can have single address instructions, like, for example, so that's a new Zoom feature and I hate it. It always tries to interpret my lines and to draw something cool, but I don't know how to make it cool. It always looks weird. So single address instruction. We have the instruction and we have one operand. And an example is for here on the right side, increment A. increment A means that we add +1 to the accumulator. So we have only one operand. A double address instruction needs 2 operands. And here on the right side is an example from x86 architecture. You can state move AX hexadecimal 50F4. Then we are copying this hexadecimal value to the register AX. So we have 2 operands, therefore we call it double address instruction. And last but not least, here we have a free address instruction. We have 2 operands and we have the target to store the result. And this we have seen in the ARM instruction set in the last weeks. So if we write add R2, R4, R5, then the sum of R4 and R5 is written to R2. Of course, you can imagine that a 0 address instruction is much easier to interpret and execute than a free address instruction. Now that's obvious because if I've got 2 operands and a target for the result, I have to prepare all of the operands. I have to move the result to the target and so on. And this must all be realized by the control unit. So this is much more complex than simply invoking an instruction without any operands. So this is one characteristic how commands can be distinguished. The second one is the length of one instruction. So we have seen instruction sets with variable length of commands, and we have seen instruction sets with a fixed length of commands. So for example, for a fixed length, each command is stored with 2 bytes. So your program code, each instruction is stored with 2 bytes. And if your main memory, the width of your main memory is 1 byte, that means you need 2 lines per instruction. 2 lines per instruction. And your program counter is incremented by 2 after execution, right? So you always go 2 lines ahead. Or we can have instructions with variable length. That means we have some instructions that are encoded with 4 bytes, and some instructions are encoded with only 1 byte, and some instructions are encoded with 2 bytes. So the left side offers more flexibility and the potential for optimization within your control unit, but it's more complex to design the control unit. And the right side leads to more straightforward, to an easier implementation of the control unit. But there is no space for optimization. You always need 2 bytes for all of the instructions, for very easy ones and also for very complex ones. You always consume 2 bytes. Okay. Questions by now? No? Okay. Then we take a look at the control unit within our 4-bit CPU. On slide 77, we see the schematic for the control unit for our own CPU. I've told you that Heinz Endres has realized the complete CPU in Altium, so it works completely within the simulation, but he still seeks a student that realizes this in hardware. So if you're interested in, so to say, hardware, software, co-design, and you want to realize this simulation in hardware, you can simply ask him. Maybe you can do a bachelor thesis with him. And he has already prepared this in Altium as a simulation. And this is a screenshot from his circuit. And we don't have to go into the details, but I want to show you that here again, we find dedicated components for our data memory, for our program memory, for the control unit, and for the ALU. So he has designed the ALU based on the concepts that we have discussed in the last week. So 4 times a 1-bit adder produces a 4-bit adder, and then he has implemented the ALU functionality in this block, ALU inst. He has implemented the control unit functionality in this DU inst here in the middle, and he has implemented data memory and the program memory. We can take a short look. So for example, you know, or we have already seen, and we will now, in a second, we will do this in detail, but we have already seen that we have 2 registers, each register with 4 bits. And of course, it must be possible that we connect the ALU with the registers. We have to connect the ALU with the registers. And this is, for example, this connection here. So we have 2 connections between the control unit and the ALU. And A and B is the label or the name of this connection. And in brackets, you see the bit count, how many bits are connected between the 2 sides. So here we have 2 bits enumerated with 0 to 3. And the result of the operation, so what the ALU has executed or calculated, is offered by another connection line with 4 bits. For R stands for result. And this connection line here, this result line, is connected. I go back here, I follow the solid line here, is connected here to the result input of the ALU. The result input or the result output from the ALU is connected to the CU. That means in the end, the result that it's produced can directly be seen and can directly be used by the control unit again. Here we have some control lines that were the control lines that trigger the functionality of the CPU. Can you remember from last week? We have to switch between different modes of operation, and this is done via the control lines. We had 5 control lines. We have connections for carry, and we also have connections to the left side of the circuit. So for example, we have here 2 memory components. 1 memory component to store the data and 1 memory component to store our program code. The 4-bit CPU is a Harvard architecture. And if we want to read data, the data is offered via this connection line to our control unit. And to select one specific line in the data memory, we have to address this line. And therefore, we have here an address input. And this address input is, or the address on the address input is given by the control unit. So the control unit says, okay, give me the data under address 50 or 10 or whatever. And then I can read this data via this data read connection to the control unit. The RW input distinguish between read and write operation, because I can write to my data memory or I can read from the data memory. So I have one bit to distinguish between read and write. And yeah, I've got a common clock. I have clock input for the data memory for the control unit. This is shown here on the left side. This is the common clock. And I've got a reset input. The reset input is necessary to start over if the system has been stopped or if the system has been broken down. So the reset input is in the end the physical button on your PC to start over if there was a problem. And resetting your PC means that the control unit in the middle starts again at a dedicated position, oftentimes memory location 0. So it starts again with memory location 0. It reads the first instruction from the program memory and then tries to execute this instruction. The instructions are represented with 8 bits, and these 8 bits are fed via data to our control unit. So if you power on this PC, this CPU, the control unit first reads an instruction from the program memory, then it interprets the instruction and reads the necessary operands from the data memory. And after this, it uses these operands together with the instruction and switches the ALU at the right side to a specific mode of operation. And then the result is written back to the control unit, and the control unit has to decide what's the next step. Write the result back or go ahead with the operation, and so on. Okay. What do you think? Is the overall idea is clear to you, or?
I think I've got a good idea about it. Yeah.
Okay. Good. So now we want to understand more details. Okay. Up to now, we only see black boxes. We only see integrated components. We cannot understand, okay, how does it work in detail? And some of the details I try to explain on the next slides. Okay, first of all, we need an instruction set. That's a good starting point. Of course, you can directly start with implementing the circuit and implementing the components, but that's very hard. That's only possible if you are a very experienced engineer in this domain. Then you can start directly with the circuit. It's easier if you start with the instruction set, because the instruction set, this is your interface to the developer. So you define, okay, which instructions should be available for your developer, and based on these instructions, you design, the control unit and the necessary components. Therefore, we start here, slide 78, with the instruction set. And yesterday in the lab, I've already told you this is the most important slide in this chapter, because this is your reference how to work with this 4-bit CPU. So if I ask you a question, a good starting point is always this slide. So yesterday in the lab, I have explained to you the different instructions. I will repeat some of the details, but I try to focus on different things today. Yesterday, I completely skipped the encoding, the coding of the mnemonics. And the coding of the mnemonics in this instruction set is relevant to us. I've told you for ARM, it's not relevant. I will not ask you about ARM coding, but I can ask you about the coding for our own 4-bit CPU, because then I can check if you have understood the concepts and if you have understood the dependencies between the components. And therefore, we take a look here at the coding and at the instructions. So let's start with our LDA and LDB instructions, Load Register A, Load Register B. We can use here an immediate value, a constant value with hashtag. And on the left side, you always see the corresponding encoding in machine language, so the bit patterns. And you see LDA is encoded with 0, 0, 0, 0, and LDB is encoded with 0, 0, 0, 1. The remaining bits are used to encode the constant value. And depending on the bits, the minimum and maximum constant value can be determined. So what's the minimum and maximum constant value for this immediate one here? What can I encode? What's the smallest number?
0.
0? 0?
It depends if it's really unsigned or signed.
Exactly. So we start with unsigned, then we have 0.
Unsigned, then 0, and the greatest would be 1, 0, 2, 3. Or is it 5, 1, 12? Or 5, 1, 2, 5, 1, 1?
Would be 15, I guess.
Oh, 15. Wow.
We have 4 bits. We have 4 bits. So 2 power 4 is 16, and we can count from 0 to 15, okay? So this number range depends directly on the number of bits that are available for this instruction. We only have 8 bits. The overall number of bits is 8. And we need 4 bits to encode the instruction, and we have 4 bits to encode the operand. And therefore, we only can represent the numbers from 0 to 15, or if we do it signed. If we use signed numbers, then
-8 to 7.
exactly, from -8 to +7, okay? 0 is a positive number. Yesterday, one student asked me, I'm not sure, how can the CPU distinct between signed and unsigned? Is there a switch to say now calculate signed and now calculate unsigned, or is there a flag, or how is this distinction done?
It's set by the programmer already, like it's preset.
Yeah, and which command? What do you mean with its preset? Maybe you think the right thing. I'm not sure.
Like it's set by the developer that these bits are only for unsigned integers or for unsigned integers, and then the very left bit tells us if the number would be positive or negative.
Yeah, exactly. So there is no switch or no mode for signed, unsigned. You cannot distinguish between signed and unsigned because you see always the same bit pattern. So if you see 1001, this can be an unsigned or a signed number. It depends on how you handle the bits. And I think that's what you've meant with it's a preset by the program. So it's up to you as a programmer if you handle numbers signed or unsigned. If you only work with unsigned numbers, then you can count from 0 to 15. If you work with signed numbers, you can count from -8 to +7. But handling of signed and unsigned is up to you as a programmer. The interpretation is up to you. For your CPU, it's just a bit pattern. There's no difference. So you can state, for example, LDA immediate 4 or LDA immediate -3. For each a bit pattern is created. A 4 is 0, 1, 0, 0, and a -3. This is 0, 0, 1, 1, inverted 1, 1, 0, 0, 1, 1, 0, 1. So 2's complement for -3 is 1, 1, 0, 1. But both are simply bit patterns. So the interpretation is up to you. So keep this in mind if you write your programs, that you have to handle if this is signed or unsigned. Okay, then we have LDA, LDB for memory cells. The memory cells are encoded, if you look here at the left side, the memory cells are again encoded with 4 bits. And with 4 bits, how many memory cells can you encode?
16.
16. 2 power 4. 2
Yeah.
power 4 from
16.
From 0 to 15, but 16 different memory cells, exactly. So the memory that you can address is very, very restricted. There is not the memory cell 100. You can only address 16 different memory cells. So you see now directly that the length of the instruction and the number of bits directly determine how many main memory you can use. If you have only maybe 5 bits for memory addressing, then you cannot buy 1 gigabyte of memory. It cannot work because you can only address a small part of this big chunk of memory. Good for store, it's the same. Of course, the number of bits for store and load are the same. If I can address 2 power 4 memory cells for reading, then I should also address 2 power 4 memory cells for writing. So we have the same number of bits. Then we skip the arithmetic ones. Do this second. We take a look at the addition. The addition also uses 4 bits for addressing. And then we have 3 commands for branching. And now we have a small difference here. You can see that for branch 0, we have 5 bits. For branch not 0, we also have 5 bits. But for branch, we have 6 bits. We have 6 bits. And therefore, the address range that we can or the distance that we can use to jump ahead and backward is of course restricted by this number of bits. So if I've only got 5 bits to address branch 0 or branch not 0, then I've got 2 power 5 that are 32 different combinations. So I can jump 16 lines backward or 15 lines ahead. So this is always a signed number. This is always a signed number. Okay, This is a signed one. So I can jump ahead or backward. And for branch, I've used 6 bits. And with 6 bits, I can address 2 power 6, 64 memory cells. Therefore, I can jump 32 lines backwards and 31 lines forward. But because my entire memory only offers 2 power 4 memory cells, of course, if I use the biggest possible number here, then I get a problem. I will address a cell that's not available. So I have to use numbers that make sense in this case. So something between -16 and +50. Okay. So these are the storing, reading, and branching operations. Is this the reason why it says upgradable up to X gigabytes, mostly by RAMs? Yeah, exactly. So if you buy a new PC and you have a standard desktop PC, then it comes with 8 gigabytes or 16 gigabytes, and somewhere in the spec you will find a note maximum memory capacity 32 gigabytes or something like this, right? And this capacity, this maximum capacity, is determined by the highest memory address that can be used. So of course you can push in new memory chips if there is a socket, but if your system, your architecture is not able to address the memory, it makes no sense, right? So the architecture determines how many memory can be used. So, and this upper bound is also increased year by year. So I know restrictions 8 gigabytes or 4 gigabytes. My first restriction was 4 gigabytes, 8 gigabytes, 16, and so on. Today, sometimes we have 64 gigabytes, but it's really restricted. It depends on the architecture. So addressing is one thing, and timing is another thing. If you buy a real memory chip, then you buy SRAM or DRAM or DDR-RAM or something like this, and these RAM components are clocked with a specific frequency, and this frequency must be compatible with your main board frequency. So the overall capacity is a restriction, but also timing if you buy some memory chips. Okay, so now we have to take a look at the right half of the table, the arithmetic and logic operations. Why is here this cutout of the main table? One reason is that otherwise it will not fit on a slide. That's the more practical reason. But the arithmetic and logic operations are encoded in the same way. All arithmetic and logic operations start with 0, 1, 1, 0. And then we have to add 4 additional bits. And these 4 additional bits here, C, 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 are outlined here on the right side. So for example, if I want to execute a XOR, let's do XOR, A XOR B, then this is encoded with 10, 10. This bit pattern has been added here. So XOR is encoded with 8 bits. An add is also encoded with 8 bits. 0, 1, 1, 0, 0, 0, 1, 0. So the logic and arithmetic operations, all of them need 8 bits for encoding. how many instructions can be encoded at all within this CPU. How many instructions are supported? If you can wish new instructions, how many possible instructions are available?
256.
So we have 8 bits for the encoding of one instruction. Therefore, we can encode 256 different instructions. And you see, we have only used a very small subset, right? We have 1, 2, 3, 4, 5. So we have 12 here and here, some more. We have 25 instructions or something like this. Yeah? So we only have used 10% of all of these instructions. Yeah? We've only used 10%, but these instructions are sufficient. Yeah? You can solve all problems with these instructions because they offer you full computability. Yeah? So you can solve all problems that can be solved. In computer science, there are some problems that cannot be solved in deterministic time or at all, but the most standard problems, so the daily life problems, can be solved also with this very reduced instruction set.
So what are these 8 bits of? Like, what's the component which has these 8 bits?
The 8 bits are one memory cell in your main memory, because you write in one memory cell one instruction.
Mhm.
And also the CPU has to handle the 8 bits, because the CPU must interpret it and execute the corresponding operation.
So it depends on the CU how many instructions can be implemented. Then.
Yeah.
Okay.
The CPU supports a specific set of instructions. And this set is determined by the number of bits that are available to encode one instruction. An example for write instruction using lend or SOR. Yeah, that's very easy. You can simply write. That's it. Because logical AND always combines A and B. You don't need an operand because there is no option for an operand. You only have 2 registers. Therefore, a logical AND must be between A and B. So you can simply say logical AND, logical XOR. You don't have to state the register. Yeah? So in the lab and in the exam, the only thing that you are allowed to write is shown here in the column instruction. This is the syntax that you have to follow. And here on the right side, same. This is the syntax. You are allowed to replace i's and m's, so everything in angle brackets, with a real number, with an integer number, but everything else must be written as given there. No? So this, I hope you know this notation. I'm not sure if I've mentioned this. If you see something something like this in a manual or in a textbook, then this is simply a placeholder. A placeholder for a value, for an integer value or for a real value, whatever. So these angle brackets mean put in here a number or a letter or whatever. So you have literal symbols that you have to write as is. So you have to write LDA, brackets, placeholder, brackets, and in this syntax you can replace angle M with a number. And the allowed numbers are determined by the number of bits. In this case, 2 power 4, 16 combinations, so we can add numbers from 0 to 15. Okay. So that was the instruction set, and that's the last slide for today, because for this I need a little bit more time. The instruction decoder. So now we want to understand, okay, how does our control unit interpret an instruction? So how does it recognize the instruction? And this is shown on the next slide. The interpretation of the commands is done by the instruction decoder. The instruction decoder interprets a bit pattern and executes the corresponding operation. And we have 3 examples. 3 minutes, 3 examples. I do my best. We want to execute LDA immediate I. LDA immediate I. The encoding for LDA immediate I is shown here on the left side. We have 4 times 0 and 4 bits for the constant value. If we want to recognize this, we have to ensure that the first 4 bits are all zeros. And we copy this command to our instruction register, and now we have to check if the first or the last, depends on the perspective, if the last 4 bits here, if these 4 bits are zeros. And the easiest way to check this is an AND gate with inverted inputs. So if all of these bits are zeros, then the inverted inputs are all ones, and this AND will produce a 1. So the idea of the instruction decoder is for one input pattern, it produces exactly one that triggers a specific functionality. So for this input pattern, 0, 0, 0, whatever, here a 1 is produced, here a 0, and here a 0. If I change the command, if I use, for example, store A with a memory cell, then this is encoded with 0, 1, 0, 0, and 4 bits for the memory cell. This can be recognized via an AND gate where the bit 7 is inverted, the bit 5 is inverted, and the bit 4 is inverted. The bit 6 is used without an inversion. So for this bit pattern here, the instruction decoder will produce a 1 here and a 0 here and a 0 here. And then I can trigger store A. And last but not least, an addition is encoded with 0, 1, 1, 1. So therefore, I need an AND gate again. The bit 7 is inverted. All other bits are used directly. And this will produce a 1 here and a 0, 0 here. So this instruction decoder is only a part. It's not the entire instruction decoder for our instruction set, because this one only decodes 3 instructions. It can recognize LDA, SDA, and M. The remaining 20 instructions are missing here. And I will ask you in the exam about the remaining ones. Okay. Not all of them, but maybe a selection. Is this approach clear, what I've done here?
Yes. Okay.
Yeah, it is clear. Although I did have the question, do we require additional hardware to convert from the typed instruction to the machine code?
From the typed instruction to the machine code, from the mnemonic to the machine code.
Yeah.
No, you don't have additional hardware, but if you have a very low-level system, you cannot type in mnemonic you have directly to type in the encoded command. You have to write machine language. If you have a real-world assembler environment, then you type the mnemonic and you have a compiler. The compiler is realized in software, and this software translates each command to a bit pattern for you, because it's very annoying to do it by hand, right?
So in our case, the decoder would be on a piece of paper, and we would manually enter the machine code.
Yeah, exactly. You first write your mnemonic, and then you do the encoding by hand.
Okay, thank you.
So the first assembler code that I've written was at high school, and this was an 8081 processor, I think. It was an experimental box, and on the top of the box there was a 7-segment display with 4 positions, hexadecimal representation, and there was a keypad with 0 to 9, A to F. And our teacher gave us exercises that we have to solve, and we have to translate it to machine code, and then we put in the machine code with the keypad and with hexadecimal encoding, and then we press execute, and then we hope for the best. Then we hope for the best and see if our program was working or not. Yeah? But these times are over today. Today you have tools, and the translation is done for you directly by the IDE. So last question for today, and then I'm benching. You see here the instruction decoder uses the bit patterns to interpret the commands. What do you think? Is it possible that I define a command, for example, like this? So it starts with 0, 1, and then I've got 6 bits for an operand or something like this. If I use this approach, can I do it like this? Or maybe is there a problem?
It's definitely a problem.
Why?
I can say that, because for the processor won't know if to, like, at least it won't know how if to execute STA or ADM to start with.
Yeah, exactly. So you have a clash. Exactly, you have a clash with both. You have a clash with this, and you have a clash with this. Because if I define a command that uses a prefix, a part of another command, then our instruction decoder will recognize this command. It has no name. You can mention a name, but it's possible that at this position, at XX, I will see a 0, 0 in the operand. And this means that this can be a different command, or the 0, 1 command with an operand. So that's a design problem. You have to prevent that a prefix or a substring of your encoded instruction appears in another instruction. And if you take a look at the previous slide, that hopefully is never the case in this encoding here. So you always get an unambiguous interpretation. So that's enough for today. Final questions from your side? No? Then I wish you a nice weekend. We will see you next week in the lab, okay? Tschüss. Bye-bye.
Take care.